Hello, this is Jack Jackson. In this video, we're going to be talking about some functions, and we're going to give you some characteristics of the derivative, or maybe the derivative and the second derivative, or maybe the function itself, and ask you to kind of come up with the function or interpret it in context. So here's an example. So let f of t be the temperature in degrees Fahrenheit at a time t in hours where you live. And suppose that at time t equals 0 you feel pretty hot. So describe the shape of the graph and explain what happens to the temperature if you know this. F prime of 0 equals -2 and f double prime of 0 equals 4. So describe it in terms of just sort of generic things in the function, but then also describe it in terms of the context of the problem here. So see if you can explain this. Press pause now. Well, let's see here. This says first of all, the first derivative is negative, so it says the function is decreasing. So it's getting cooler. So good news, if you're uncomfortably hot, it's getting cooler. The second derivative is positive, so that means the original function is increasing, the derivative is increasing, and the original function is concave up. So what do we have? So we have a decreasing concave up function, so the temperature is decreasing, but at a decreasing rate. Since the first derivative is -2, that says that from this particular time, you can expect it to drop about 2 degrees Fahrenheit in the next hour, but the next hour after that, it's going to drop a little less. All right, what if we change it? What if we make f prime of 0 equals 2, but f double prime of 0 equals -4? Same basic setup, but different information here. Okay, well, let's see what we've got this time. Well, this time, the function is positive, so the derivative is positive, so that says that the function f is increasing. Okay, what does that mean? Well, that means that the temperature is rising. Well, you're hot now, you're going to be even hotter later. Okay, what about the second derivative? The second derivative is negative, so that says that the derivative is decreasing and the original function is concave down. So that says the function f is increasing, but in a concave down manner. So we can expect it to go up about 2 degrees in the next hour, but the next hour after that will be a little bit less than 2 degrees in increase. Alright, how about this next one? Next one here. Same scenario, but this time f prime of 0 is again 2, but f double prime of 0 is +4. Well, okay, the first derivative is positive, so once again the function's increasing. So this says that the temperature is going up, and again at about 2 degrees Fahrenheit per hour. So in an hour from now, we can expect it to be about 2 degrees hotter than it is now. But this time, the second derivative is positive, so the derivative is increasing, and the original function is concave up. So the function f is increasing and concave up. So that says that it's going to increase a little more than 2 degrees the next hour. So the first hour is going to go up around 2 degrees Fahrenheit, and then the next hour from that, it's going to go up a little bit more than 2 degrees. So getting hotter, increasing at an increasing rate. Okay, how about this one? F prime of 0 equals -2, and f double prime of 0 equals -4. Well, this time we have a negative first derivative, so the original function is decreasing, and it's decreasing at about 2 degrees Fahrenheit per hour, so we expect a drop of about 2 degrees in the next hour. The second derivative is negative, so the original function is concave down. So the original function is decreasing and concave down. So it's decreasing and concave down. It's decreasing at an increasing rate. So it's going to drop about 2 degrees the first hour, and it's going to drop more than 2 degrees the next hour. Okay, what if the first derivative is 0 and the second derivative is -4? All right, when you have a derivative of 0 and a second derivative non-zero, you're at an extremum. Okay, so the first derivative is 0 says you have a horizontal tangent line. The second derivative is negative says the function is concave down. Concave down and a horizontal tangent line means you're at a maximum. So we're at a local maximum. It was cooler earlier, it's going to be cooler later, it's the hottest, it's going to be at least nearby for times close to now. And of course this one here, the first derivative is 0 and the second derivative is 4. So second derivative is positive, says the function is concave up. But we have a horizontal tangent line, we're at a local minimum. Okay, so it was decreasing right before this and it'll increase right after this. It's at a local minimum. It's the lowest point for times near now. What if they're both 0? Okay. I'm sorry. What if the first derivative is non-zero and the second derivative is 0? Well, with the second derivative 0 and the first derivative is non-zero, then the original function has an inflection point. So, so that means the derivative is at a local extremum, and the original function has an inflection point. So let's see what's happening here. So the function is increasing instantaneously at a rate of about 2 degrees per hour, but it's an inflection point there. And here we have the derivative is negative, and this is positive. So back up here on this g, the function is increasing, but it is at an inflection point. And this one, the function is decreasing, but it's at an inflection point. Okay, so that gives you some interpretations there when I tell you something about the signs and the size of the first derivative, and mainly the sign of the second derivative. That tells us something about whether the function is increasing, decreasing, constant, concave up, concave down, or linear, and it tells us something about when we're at local extrema or when we're at inflection points. So some interesting things that we can see what that tells us about the graphs, and then what that tells us about back in terms of reality. So oftentimes in mathematics, whether that's pre-calculus or in calculus, we're going to look at graphs, and the graphs, of course, are points that are, vertical and horizontal distances from the origin. But those vertical and horizontal distances on the graphs, okay, or the table of numbers for x's and y's, or inputs and outputs, whatever letters we use for them, they have some meaning in the real world. So even though these are just numbers in one sense, in another sense, these numbers have a definite meaning. So this 0 is a time now, and this number here is a rate of change in the temperature.